Here's a problem on inverse functions using logarithm and exponential. We have the function f of x equal to natural log of x minus e to the x. First, I want to show that f of x has no inverse function. Then, we want to change the domain of f of x so that there is an inverse function. Finally, I want to find f inverse at 1. Now, for the first part, I want to show that f of x has no inverse function. We want to show that f is not 1 to 1, or that the graph of f fails the horizontal line test. So that means we can find a horizontal line that cuts the graph of f of x in 2 or more places. Now, before we do that, let's review the graphs of natural log of x and e to the x. For natural log of x, we need 4 items. So I know the value of natural log at 3 points and that natural log is a vertical asymptote at x equal to 0, so the y-axis. Now, the 3 points, natural log of v is equal to 1, natural log of 1 is equal to 0, natural log of e inverse is equal to minus 1. So note, if I have e to the minus 1, the exponent rule for logarithm says I could pull the minus 1 out in front, then I just use natural log of e equal to 1. For practical purposes, e is roughly 2.7, so e inverse is equal to 1 over e, which is roughly 1/3. So we plot our 3 points, we put our asymptote in, and then we get the graph of natural log of x. For e to the x, same idea. We can either memorize 4 items, okay, e to the x at 3 points, and that we have a horizontal asymptote on the x-axis, or we could just note that natural log and e to the x are inverse functions. So all I have to do to get the graph of e to the x is to flip this graph and the line y equals x. Now, what about the graph of f of x? First thing we note, what's the domain of f of x? Well, the domain is going to have to be where both e to the x and natural log of x are defined. So, if we start putting values of x through here, okay, for e to the x, I can use any real number, but for natural log of x, okay, you note it's only going to make sense if we use x greater than 0. So that's going to be our domain for f of x. Now, to show that we fail the horizontal line test, we have options. So if you feel good about end behavior, you don't need the whole graph. I just need to check what's happening near 0 and as we go out to plus infinity. Now, you'll note if we're near x equals 0, for natural log of x, we have a vertical asymptote going to minus infinity. For e to the x, we're just near the value of 1. So that means if we take the difference here, we have a minus infinity minus a 1. We treat that as a minus infinity. So in our graph, we're going to have this vertical asymptote at x equal to 0, running down to minus infinity. What happens as we go out to plus infinity? So we go all the way out to the right. Well, again, we look at our graphs. For natural log of x, as we go all the way out to the right, this is going to go to plus infinity, because it's going up that way. For e to the x, that's also going to go off to plus infinity. When I put a minus sign in front of it, it's going to go to minus infinity. So what's going to happen is I have a plus infinity plus a minus infinity, which is, okay, indeterminate. It means we need to do more work. Now, if we take a look at values as we let x get large for natural log of x and e to the x, okay, we note natural log gets to plus infinity very slowly. E to the x gets there very fast. So I take the difference, okay, our limit is going to go off to minus infinity. So as we go out this way, okay, we're going to have something that's pointing downwards. Now you'll note if I have something pointing downwards near x equals 0, and as I go off to infinity, okay, we're going to have sort of a bowl shape, and we're not sure what's happening in the middle. But just from the end behavior, we know that we're going to have a horizontal line somewhere that cuts the graph in at least 2 points or more. So we're going to fail the horizontal line test. Now, if we're not entirely comfortable using the end behavior, we can instead get an idea of the graph by using the derivative of f of x. So we'll take the derivative of f of x, we'll look for the critical points, then we'll find the regions of increasing and decreasing. Now, we have our function f of x. If I take the derivative, natural log of x goes to 1 over x, e to the x goes to itself. If I want critical points, they occur where our derivative is equal to 0 or does not exist. If the derivative doesn't exist, that can only happen when x is equal to 0, but that's not in the domain of the original function. So we can ignore this case. That means we want to know where the derivative is equal to 0 or where 1 over x equals e to the x. Now this equation we can't solve in closed form, so we're going to need to approximate instead. Now, to find the number of solutions to this equation, I'm just going to graph each function and then see what the intersection is. So 1 over x looks like this. Here we have the graph of e to the x, and these graphs intersect at exactly 1 point. So we have exactly one solution and exactly one critical point for f of x. Now, if I want to get an approximation of this point, first let's get an idea of what region it lives in. So to do that, we're just going to evaluate our derivative at different points. If we take the derivative evaluated at point 1, we get roughly 7.18. And if we evaluate our derivative at 1, we get roughly minus 1.72. Since our derivative is continuous when x is greater than 0, that means, okay, if our values are going to go from 7.18 to minus 1.72, we're going to have to go through 0 somewhere. So that means our critical point is going to be somewhere between 0.1 and 1. Now, if I want to narrow that down, we can go to one of our approximating methods like the bisection method or Newton's method. So if we iterate a few times, we'll see that we're going to have our critical point settling on, okay, roughly 0.567. So that means the derivative evaluated at 0.567 is roughly 0. Also going to want to know the value of our original function at 0.567, which is minus 2.33. So that's going to give me a point on the graph of our function. Okay, so here I have the graph of f of x. Okay, we have our critical point. If I'm interested in regions of increasing and decreasing, okay, I'll put a box in here. I'm going to split the box at our critical point, then determine whether we're increasing or decreasing on each side. It's enough to check our derivative at 1 point. Now, for point 1, which is going to be in this region, we get a positive value for the derivative, so we're going to be increasing on the whole region. On this side, okay, we're going to have 1. The derivative is going to be negative at 1. So that means we're going to be decreasing on this entire region. So if we connect the dots, okay, we see not only do we have a local maximum here, we're going to have an absolute maximum for our function, okay, of roughly minus 2.33. Now, what we were interested in, horizontal line test. This is going to fail the horizontal line test if we check, say, the line y equal to minus 3. Okay, so it's going to be going down here. That's going to cut our graph in exactly 2 spots, so it fails. That means our function is not 1-to-1, which means our function does not have an inverse function. Now, for the second part, our first part could be the end of the story, but if we discard some of the domain of f of x, we may have an inverse function for what's left over. So what we'll do is, we're going to consider the same function, but now with domain x greater than our critical point. So we're just going to consider all x beyond our 0.567 and so on. Now you'll note this function, the graph satisfies the horizontal line test, so we're 1-to-1. There's an inverse function for our f2. If I want more information, first thing we can do, if I want the graph of the inverse function of f2, I just reflect the graph of f2 through the line y equals x. So it's going to carry this arc here to an arc up here like this. Okay, so as so. Numerically, if I had a point in the graph given by x comma y, okay, where y is equal to f2 of x, I now have points on the graph of the inverse function given by y comma x. So I have at least one point now. Before we had 0.567 comma minus 2.33. That goes to the point minus 2.33 comma 0.567. If I want to find the equation that goes with f2 of inverse, so I want it as a function of x in closed form, I write f2 of x equal to y. We switch x and y, solve for y. Now when we try that, we're going to be left with this equation here, and we're not going to be able to isolate y. So in practice, we're going to be able to find values of our inverse function if we're given precise numbers, and then we can approximate. So for our third part, I was given find f2 of inverse of 1. So to get this, I can let that be equal to x. Then I'm just going to switch the x and the y. So this equation becomes f2 of x equal to 1. If I go to the graph of f2 of x, you'll note, okay, that being equal to 1 means we're looking for the point on the graph that intercepts the line y equals 1. There's no point that does that. So that means we're going to have undefined. Another way to see that, if I look at f2 inverse of 1, well, I could just look at the graph of f2 of inverse. Okay, so here, at the point 1, we're never going to cut through the graph. So again, we're undefined. Now, a better problem is to consider f2 inverse of minus 3. So if I call that x, okay, I switch our x and y. So we have f2 of x equal to minus 3. So we're trying to solve natural log of x minus e to the x equal to minus 3. Now, if I push the minus 3 to the other side, I'm going to consider the function g of x equal to natural log of x minus e to the x plus 3. We want to know when that's equal to 0. So, what we could do, same thing as before. I'm going to check 2 points to try to isolate the region where our 0 is, and then we can use the bisection method to get a better approximation. Now, if I take g of 1, put that in, we're going to get 0.28. If I try g of 1.2, we're going to get minus 0.14. So we know the 0 is going to be between 1 and 1.2. Now note, you might be wondering why I didn't go with, say, 0.1. If I take a look at the graph here, so I want to know where this is going to be equal to minus 3. Okay, so here we're looking for minus 3 as the y value. Here we're looking for minus 3 as the x value. So if I'm at minus 3 here, we know the value is going to be up here somewhere. So it's going to have to be greater than 0.567. So 0.1 is not going to be an option to check. Now, so the 1.2 I get by experimenting till I get something that has an opposite sign of the 1. Now, we know that our 0 is going to be between 1 and 1.2. So I can use the bisection method to narrow that down a little bit. So if I narrow down a little bit, we get to 1.14 approximately. And then I can check by just sticking into our equation. So if I put that into natural log of x minus e to the x, we get a number that's roughly minus 3, which is what we're looking for. Now, had I went with 0.1, our x was going to be equal to 0.1612. And that's going to be our solution if we restrict our domain to x between 0 and 0.567. So this number, you'll note, is not going to be in the domain of our inverse function for f2.